This is lesson 3.6c. In this, we're going to continue to talk about slope and slope-intercept form. In example 1, it says a linear function g models a relationship in which the dependent variable, remember dependent variable like we mentioned before is the y variable. So the dependent variable increases 3 units for every 1 unit that independent, remember independent is our x variable, the independent variable increases. Graph g when g of 0 equals 3. Identify the slope and intercepts of the graph. So a couple things we have to think about. When we're trying to find slope, remember that we have our formula where we have the change in the y value. So change in y over change in the x values. Suppose it would help if I wrote the y up here. There we go. So change in y over the change in x equals our slope. So if we look back at the problem, this says that the dependent variable increases 3 units. So the change in our y value is 3. And then it says that every time the y increases by 3, the x or the independent variable increases by 1 unit. So the change in our x value is 1. So if we simplify this, 3 divided by 1 is 3. And that's our slope.
So you guys still down to rehearse at my place?
They also
Yes,
want us to figure out
Is it cool if I
the
bring
intercept,
Stacey?
right? The x-intercept, the y-intercept.
Yeah, Giselle wants to come too.
Intercept. The y-intercept is when x equals 0. So if they give us the information that g of 0 equals 3, they're telling us that x is 0, and when x is 0, y is 3. So our y-intercept is 3. Or if we're thinking about it in terms of a point for the graph, 0, 3. So we're going to plot that y-intercept 0, 3. And then I also have to figure out my slope, or figure out my x-intercept, and I'm going to use my slope to do that. So remember that my slope is 3 over 1. Now, here's the thing. If my y-intercept starts here, and I move up 3 and right 1, up 3 and right 1, because all those numbers are positive, am I ever going to touch the x-axis if I continue in this pattern? I'm not. So I'm going to do one just to show you. So I'm moving up 3, so 1, 2, 3, and over 1, and I'll put my dot right there. But if I kept going in that manner, I'm never going to hit the x-axis. So something I want to show you. Think about your multiplication and division rules. When we multiply or divide two positives by each other, so positive divided by positive, we get a positive answer. So what if I rewrote my slope as -3 over, because fractions mean division, over -1. -3 divided by -1 still gives me +3 for my slope. So not only do I have a choice to move up 3 and right 1, I can also choose to go from my y-intercept. I can go down 3 and left 1. 1, 2, 3, and left 1. So it stays right in line with my other points as it's supposed to, but I can just show it in a slightly different way. And that helps especially if we have a graph that we're given and maybe moving up causes us to run out of space. Or maybe we have a negative slope and moving down causes us to run out of space. It's interchangeable as long as my positive slope still simplifies to that same positive slope. Or if it was a negative slope, that it still simplifies to that same negative slope. So as a result, it looks like we're crossing the x-axis here at -1, 0. So our x-intercept, remember that's when y equals 0. So for that one, our x-intercept is -1, or the point -1, 0. All right, let's take a look at example 2. Example 2 says, a submersible, I like to think of it as like a submarine, a submersible that's exploring the ocean floor begins to ascend. Think about ascend, that means that we're moving towards the surface or going up. So ascend to the surface. The function h of t equals 650t minus 13,000 models the situation where h of t is the elevation in feet of the submersible, t minutes from the time it begins to ascend. So what we need to look at is, we're going to graph the function and find its domain and range. And then we're going to interpret the slope and the y-intercepts of the graph. So what I need to do first is, I'm going to write my function here. And I want to make a connection with you. If you notice, it kind of looks like it's already in a form of slope-intercept form. So because of that, we know that our y-intercept is -13,000. So it looks like each of these lines is counting by 3,000. So we're going to have to be just below that -12,000, so about right here. And we know that they're going up 650 feet for every minute since they've begun their ascent. So if I'm looking at this, I have to figure out when are they going to cross the surface, all right? How many minutes is it going to take them to get to that surface? So the first thing I'm looking at is, how do I get from 650t minus 13,000 back up to 0? So if I want to know, when is it going to be 0? This is my x-axis. So I need to know when y is 0, what is x going to be? And I know that I'm going from -13,000 up to 0. So if I'm looking at my range, I know that my range, the lowest value is -13,000 because that's where they started. So it has to be greater than or equal to that. But I also can only get to the surface. I can't like jump out of the water with my submarine. So the surface is where they're heading towards. So 0 is the highest and negative 13,000 is the lowest value that we're looking for here. So if they move for 0 minutes, then they haven't gone anywhere. They're still at negative 13,000 feet. So I know that the lowest amount of time that they can have is 0 minutes. But I need to figure out what is the maximum amount of time that they can do. So if I plug in 0 for y, or for h of t in this case, then I would have 0 equals 650t minus 13,000. So I'm going to solve for t. So I'm going to add this 13,000 to both sides. So I have 650t equals 13,000. I'm going to divide both sides by 650. And I find that the maximum amount of time that it's going to take for me to get to the surface in my submarine is 20 minutes. So the maximum for our domain is 20 minutes. Because after 20 minutes, we're at the surface. Like I said, I can't jump out of the water, doing all these tricks on the submarine outside the water. Once I get to that surface, then I'm done. All right, so what we have found, we have to graph that. So after 20 minutes, we were at 0 feet. So 20 minutes, 0 feet. There we are. We can graph our line. I'm not going to go past those because, again, once I get to the surface, then I'm done. And I started at negative 13,000. I didn't go lower than that. So I'm going to just stay between those two dots. Part B says, interpret the slope and the intercepts of the graph. So our slope is 650. Notice I don't include the variable. It's just the 650. And what that means is that the submarine goes up 650 feet every minute. So sub goes up 650 feet per minute. Then if I look at my y-intercept is negative 13,000. And that is how deep the sub is before they start going up. So this is our depth before the ascent. And then our x-intercept, or in this case, they call it t, right? Our x-intercept here is 20. And that 20 means that it takes 20 minutes to get to the surface. So sometimes it's not important only to know what the intercepts are, what the slope is. We have to be able to make sense of what they mean in terms of our problem. In 3.8a, in this lesson, we're going to be talking about absolute value functions. And an absolute value function is basically a function that has an absolute value in it. A couple of things I want to point out to you. In an absolute value function, the graph is V-shaped. It's also symmetric about the y-axis. So for specifically the f of x equals absolute value of x, that one is symmetric on the y-axis. Now, some of them you're going to find are still symmetric, but not necessarily on the y-axis. But they're always V-shaped if they are absolute value. And if you think about it, if we take the absolute value of positive 2 or the absolute value of negative 2, we're still going to get 2 because they're both 2 units away from 0. So, excuse me. So all absolute value functions are symmetrical, but it just depends on where their line of symmetry is, depending on the function itself. For this particular graph right here, the domain for f of x equals absolute value of x is all real numbers. And the reason for that is because this graph is going to continue on and on and on and on forever and ever and ever in this pattern. And as I continue, my x values this way are going to get smaller as my y values are getting higher. And this way my x values are going to get higher as my y values are getting higher. But remember that number lines go on forever. So in theory, this v, if we had enough paper, could go on forever and ever and ever and ever. For the range, we have that y is greater than or equal to 0. Because if it continues in this pattern, is it ever going to go below that x-axis? It's not. This vertex shows me the lowest value that I'm going to have for this absolute value function. So for my range, that value is my lowest, 0, and it's every number in the history of the world higher than that because, like I said, as the x values increase to infinity, y is also going to increase vertically forever. Those numbers can also go on forever and ever and ever. So we are going to graph these two functions down here, and we're going to compare them to our f of x equals the absolute value of x function that we have in that top part here. And then we're also going to find the domain in the range. So what I'm looking at for A, we have the function g of x equals the absolute value of x plus 3. So in order to graph this, I need to pick some values for x. And then we'll see how they impact the function itself afterwards. So I'm going to choose negative 2, negative 1, 0, 1, and 2. Sometimes these numbers will work out great. Sometimes you might want to choose different numbers. But for the sake of this one, we're just going to use these. So what I'm doing here is I'm plugging in each of these numbers for x to discover what g of x would be. So we've got the absolute value of negative 2 plus 3. The absolute value of negative 2 is 2 plus 3 gives me 5. And I do know negative 1. Absolute value of negative 1 is 1. 1 plus 3 is 4. Absolute value of 0 is 0. 0 plus 3 is 3. Absolute value of 1 is 1 plus 3 is 4. Absolute value of 2 is 2 plus 3 is 5. So here I have my points. So I have negative 2, 5, negative 1, 4, 0, 3, 1, 4, 2, 5. So what I want you to notice is we still have that V shape that we had in our original absolute value graph at the top. We we still have that same original V shape. However, this one started at 0, 0, while this one has moved up 3 spaces. So if we wanted to talk about it in terms of how it's moved, then this is a translation, because it's a slide. The translation slid it up 3 spaces. If we're going to talk domain and range, every x value in the history of the world still is possible for this absolute value function, even though we slid it up 3 spaces. So our domain is still all real numbers, just like it was with our original absolute value graph. And our range, so if we look at it this time, our range, before it was y is greater than or equal to 0, but now 0, 1, and 2 don't fit in that category. So the smallest value I have on my absolute value graph this time is positive 3. So I know for my range that y has to be greater than or equal to positive 3. Now we're going to look at our second function. For this one, we have m of x equals absolute value of x minus 2. So again, I need to make a table of values. So I have x, m of x, and I'm going to use those same numbers again. So -2, -1, 0, 1, and 2. So when I plug these in, I have -2 minus 2, and we're taking the absolute value of that answer. Well, -2 minus 2 is -4. The absolute value of -4 is 4. Then I'm going to plug in -1. -1 minus 2 is -3, and the absolute value of -3 is 3. We're going to plug in 0. 0 minus 2 is -2. Absolute value is 2. Then I have 1 minus 2, and we have 1 minus 2 is -1. And the absolute value of -1 is 1. And then we're going to keep going, and we have 2 minus 2 is 0. The absolute value of 0 is 0. But I want to show you, on this side, notice how we got to a point where there was a number that was only one of them, and then we started repeating the numbers again. We haven't gotten there yet. So what I want to encourage you, if you run into this situation because you picked numbers that you didn't realize weren't going to line up, add a couple more. So let's see what happens if we go to number 3. 3 minus 2 is 1. The absolute value of 1 is 1. Look at that. We started our numbers over again. And we'll go one more. 4 minus 2 is 2. Absolute value of 2 is 2. So notice now we've kind of started to see. So we can see that the shape that it makes, so we can be sure that it does make the V shape that we're looking for. So for this one, we have -2, 4, -1, 3, 0, 2, 1, 1, 2, 0, 3, 1, 4, 2. Now, what I'll share is that if we kept going with our list and we went all the way up to 6, positive 6, we'd end up with the same equal number of dots on each side. But once we get to that vertex point, we can connect our dots here. And we'll see that once we connect them, it does have that symmetrical look to it. It's got that V shape that we're looking for. But when we compare it to this original, notice this one, the vertex was at 0, 0. This one, the vertex is at 2, 0. So this one has actually still done a translation, but instead of sliding up like we had over here, now we're sliding to the right, which is interesting because we've got this subtraction sign in here. Most of the time when we think subtraction, we think that we would be going to the left. However, because it's absolute value, it ends up sliding it to the right, even though we have that subtraction sign in there. So a couple things we want to jot down. Oh, we got to talk about our domain and range. So our domain for this, again, all those x values would be possible. So we have all real numbers. Our range, look at that vertex, what is the lowest point vertically that we have? The lowest point vertically is 0. Even though we've shifted it to the right, it still doesn't go below 0 on the y-axis. So our range is y is greater than or equal to 0. All right, so a couple things we want to kind of take notice of when we're thinking about absolute value. If we have our function of x equals absolute value of x plus a number outside the absolute value is going to make it go up that number of spaces on the y-axis. If we have f of x equals absolute value of x minus a number, that means we're going to be going down that number of spaces on the y-axis. And when we say down, we mean that vertex point. If we have f of x equals the absolute value of x minus a number, but they're inside the absolute value, then that means that we're going to go right that number of spaces on the x-axis. And finally, if we have f of x equals absolute value of x plus a number, and again, inside the absolute value, that means that we're going to be moving left that number of spaces on the x-axis. So if you'll notice, outside of the absolute value brackets, it's what we're used to. Plus means up, minus means down. If it's inside the absolute value brackets, it's kind of the opposite of what we're thinking of normally. So minus means we go right, plus means we go left. All right, let's take a look at example 2. example 2 says graph each function, compare the graph to the graph of f of x equals absolute value of x. We're going to find the domain and range again. So for our first one, we have q of x equals 2 times the absolute value of x. So we're going to make ourselves a table here. And this one was q of x. We're going to use the values -2, -1, 0, 1, and 2. And it was q of x equals 2 times the absolute value of x. So we have 2 times the absolute value of -2. Well, the absolute value of -2 is 2. So it's basically 2 times 2, which is 4. The absolute value of -1 is 1. 1 times 2 is 2. Absolute value of 0 is 0. 0 times 2 is 0. Absolute value of 1 is 1. 1 times 2 is 2. Absolute value of 2 is 2. 2 times 2 is 4. So on our graph here, we've got the point -2, 4, -1, 2, 0, 0, 1, 2, and 2, 4. So this is our new graph. And what I want you to see, I'm going to put the original f of x equals absolute value of x. I'm going to put that graph on here as well for us. So we still start at 0, 0, and then we have a point at 1, 1, 2, 2, 3, 3. Yeah, 1, 1, 2, 2, 3, 3. So we're starting in the same location. But notice, when I multiply absolute value by 2, my graph actually got thinner. So the numbers started going up steeper or quicker than they did originally. So it looks like it kind of squeezed together for that graph right there. So if we're looking at domain and range for this, again, the domain is all real numbers. We haven't had any instances so far where it isn't all real numbers, although it is a possibility. And our range, just like with the original f of x equals absolute value of x, our range is still all those numbers that are greater than or equal to 0. All right, let's look at part B of that example. So in this one, we have the function p of x equals -1/2 times absolute value of x. I want you to think in your mind, make a prediction about what you think is going to happen to this graph in comparison maybe to the one we just did and also to the one that we started with just a plain old absolute value of x. So we're going to make our table. So we have x and p of x. We're going to use the points -2, -1, 0, 1, and 2. So absolute value of -2 is 2. -1/2 times 2. No, actually, I'm going to put that in parentheses. -1/2 times 2 is actually -1. And then -1, the absolute value of -1 is 1. 1 times -1/2 is -1/2. Absolute value of 0 is 0. 0 times -1/2 is 0. Absolute value of 1 is 1. 1 times -1/2 is -1/2. Absolute value of 2 is 2. 2 times -1/2 is -1. So interesting, this time, because our negative number was outside of our absolute value, we got some negative y values here. So let's graph them. We have -2, -1. -1, -1/2. So we're kind of like halfway between 0 and 1. 0, 0. 1 and -1/2. So again, halfway between 0 and 1. And 2, -1. All right. And now again, I'm going to put that original one on here for us. So we still had 0, 0. And I went like that. So it's a little bit subtle, but notice this one seems to be more spread out ever so slightly than the original was. But also the biggest difference that we're noticing is that instead of pointing up, like we've seen all of our other absolute value functions, this one's pointing down. So one thing I want you to take notice of is that the negative sign outside here is what flipped our absolute value to be facing down. So it took that whole thing and kind of reflected it over that x-axis. So now it's pointing in a downward direction. So it opens down if we have a number that's negative outside of our absolute value being multiplied. All right, so our domain, we still are covering all the x values, even though it's facing downwards. So our domain is all real numbers. But this time, we don't know what the lowest value of y would be, but we do know that there's a maximum on this one. The maximum y value for this one is 0, 0. So our range, this time, instead of being y greater than 0, we know that y has to be less than or equal to 0, because all those numbers that are possible below the x-axis. So in other words, below 0 vertically. Can't go up here because it's not part of our new function for that one. 3.8b. In this lesson, we're going to continue talking about absolute value functions, but we're going to talk about a special form for those absolute value functions. So the form we're going to talk about is called vertex form. And vertex form is this format right here. So g of x equals a times the absolute value of x minus h plus k, but a cannot be equal to 0. When you have an absolute value function that is written in vertex form, the h is your x value and the k is your y value for the vertex of that absolute value. Now notice in here, h has a minus sign in front of it. It's like the one time that when it shows a minus in front of it inside the absolute value that you just ignore the minus and it's h. So just like when we were graphing them, not in vertex form, when you have a minus inside here, you treat it as the opposite of what it looks like. But if it were outside, you treat it the way it is. So outside, those positives and negatives are what they are. Inside the absolute value is the opposite of what it looks like. So that vertex for this would be hk. The other thing to notice is that when your function is written in vertex form, then the line of symmetry is the number or the line x equals h. So remember from previous lessons, x equals means it's a vertical line and it's vertical through the number h, whatever that may be for that function that you're working on at the time. So let's kind of take this information and put it into practice for ourselves. So graph each function on the same coordinate plane. We're going to compare the graph of g to the graph of f and kind of have a discussion about that. So when we're looking at the function of f, what I want you to notice is that it is in vertex form. The difference is here they have their a, but just like other lazy mathematician instances, if it's not listed, it's a 1. Okay, because we know it can't be 0 in order to be in vertex form. But the function g of x is not in vertex form. And the reason it's not, notice how x is just x. Well, here it's 2x. So that makes it a little bit different in terms of whether or not it would be considered vertex form. So for that one, it is not. G of x is not in vertex form. All right, so let's take a look for f of x. We have absolute value of x plus 2 minus 3. So one thing that we know for sure is that the vertex for this, because of the way that it's written, the vertex is that point hk. So the original, remember, had the minus, so it's opposite of what it looks like here. So our vertex is going to be -2 and -3. So because we know that the vertex is going to be -2, -3 based on our equation, I like to make sure that I go a couple of numbers lower and a couple of numbers higher than that. So I'm also going to do -3, -4, -1, and 0. Because I know that this is where my vertex is based on our vertex form. So if I plug in -4 into our equation here, we have the absolute value of -4 plus 2 minus 3. Well, -4 plus 2 is -2. The absolute value of -2 is 2. 2 minus 3, -1. So then -3 plus 2 is -1. Absolute value of -1 is 1. 1 minus 3 is -2. Now, since we know that this is the vertex, and we know that it's symmetrical at x equals -2, we know that these numbers are going to start over. But let's just double check. So -1 plus 2 is 1. Absolute value of 1 is 1. 1 minus 3, -2. 0 plus 2 is 2. Absolute value of 2 is 2. 2 minus 3, -1. So we're going to use, we'll use this purple. So I know I've got the point -4, -1, -3, -2, -2, -3, -1, -2, 0, -1. Okay. Now, since g of x is not in vertex form, we don't know exactly where the vertex of this is simply by looking at it. So what we're going to do is we're going to pick some values here. So we've got our g of x equals absolute value of 2x plus 2 minus 3. So we're just going to use a few values. So we're going to do -2, -1.5, -1, -0.5, 0, 0.5, and 1. Okay, so if I plug it in here, 2 times -2 plus 2 minus 3. So 2 times -2 is -4 plus 2 in our absolute value. -4 plus 2 is -2. Absolute value minus 3. Absolute value of -2 is 2 minus 3 is -1. -1.5 times 2 is -3. -3 plus 2 is -1. Absolute value of -1 is 1. 1 minus 3 is -2. 2 times -1 is -2. -2 plus 2 is 0. 0 minus 3 is -3. And I would suggest writing these down. I'm just trying to save a little bit of space for you in your notebook here. -1/2 times 2 is -1. Plus 2 is +1. Absolute value of +1 is 1. 1 minus 3 is -2. Hey, look at that. We started our pattern over here. So I know that the next one is going to be -1. Half of 2 is 1. 1 plus 2 is 3. Absolute value of 3 is 3. 3 minus 3 is 0. 2 minus 1, or 2 times 1 is 1. Oh my goodness. 2 times 1 is 2. 2 plus 2 is 4. Absolute value of 4 is 4. Minus 3 is 1. Probably why I kept trying to say 1. All right, let's graph this one. We're going to give this one, let's make it stand out differently. We'll use yellow. So we have the point -2, -1, -1.5, and -2. And then we have -1, -3, -1/2, and -2. 0, -1, so those two dots overlap. And 1, 1. All right, so if we're taking a look at these two things here, what we're noticing is that we can actually rewrite g of x equals f of 2 times x. And the form that they mention for this is that y equals f of a times x. It's a special format that they mention. And in this instance, a happens to be 2. Okay, so it's 2 times x. We do notice that horizontally, we have a shrink of graph f by a factor of 1/2. So this purple graph f shrunk in half to be for function g. We noticed that our y-intercept is the same for both of them, right? Because they have that same spot of 0, -1. And when we look at the input values of f, so the input values for f, they're 2 times the input values of g, right? So 2 times -2 is -4, but they gave us the same output. 2 times -1/2 is -3. Both gave us the same output. 2 times -1 is -2. Both got the same output. So that's how this one is half of what that is. So this is 2 times g of x to give us that f of x. Yep, that's what I was going to say with that. So now we're going to look at example 2. We're going to graph g of x equals -2 times the absolute value of f, and that means that our vertex for this is 1, 3, right? Opposite of what it looks like, exactly what it looks like. So 1, 3 for this vertex, right there. And then we know that we need to plug in some points to be able to get the rest of this graph for us. So if my vertex is 1, 3, I know that I want to do a couple numbers below it. So I'm going to do 0, -1, and I want to go a couple numbers above. So we'll do 2 and 3. All right, so let's write these down real quick. We have the function g of x equals -2 times the absolute value of x minus 1 plus 3. So we're going to plug in -1 first. So we've got -2 times the absolute value of -1 minus 1 plus 3. So we have -1 minus 1 is -2 plus 3. The absolute value of -2 is 2. -2 times 2 is -4 plus 3 gives us -1. This time we've got -2 and then we have 0 minus 1 plus 3. So that's -1. -2 times the absolute value of that is +1. So then I have -2 plus 3, which gives me +1. And then our next number we need to work on is +2. So -2 times the absolute value of 2 minus 1 plus 3. So I have -2 times the absolute value of 1. -2 times the absolute value of 1 is -2 times 1. So that's -2 plus 3, which is +1, which we kind of already knew because of the ones we'd already done. But just to double check, so we know that when we plug in 3, we're going to get -1. All right, so let's plot these other points here. So I have -1, -1, 0, 1, 1, 3.5, 2, 1, and 3, -1. So just like a previous question in this lesson 3.8, I should say, we have an absolute value graph that is facing downwards. So a couple things we want to talk about in terms of this equation is in comparison to our original function of x equals absolute value of x, it's flipped. It has shifted 1 space to the right and 3 spaces up, and it's flipped over. So we've shifted it, we have flipped it, and it looks like it has stretched up vertically, which means it's kind of shrinking the space between it, like the width of it has kind of come together because it's increasing more and quickly compared to the original. So when you look at that function that we had originally, -1 plus 3. So this plus 3 is the reason that we translated it up 3 spaces. This -1 is the reason that we translated it right 1 space. So these we talked about being translation. And this 2 is the reason we had a vertical stretch. So it went taller. So that vertical stretch of times 2. And this negative sign right here is the reason that we had to reflect the whole graph over the x-axis. So we've seen before how a negative sign in front of our absolute value, like with that -1/2 we had in a previous example, how it flipped our absolute value graph upside down. So still the case here, that negative sign is the reason it's flipped over.